记得。Here it is already.
I'm a research scholar at Indian Institute of Technology, Delhi. I'm working under the supervision of Dr. Suresh Bhalla, Associate Professor. Topic of my video is feasibility of energy harvesting from embedded sensors in addition to structure health monitoring via B31 mode. Now, objectives are integrated SHM and energy harvesting. Considering any structure with a piezo sensor either embedded or surface bonded over it, under the vibration, charges will produce on the piezo sensor. Now, in the idle stage, any energy harvesting device will harvest this energy and store it in any storing device, and which will be further used in SHM stage for the structural health monitoring of the structure via this piezo sensor. Other next objective is the use of axial strain actuation mode. There are two modes of energy harvesting, D33 and D31. We are focusing on D31 mode, though D33 piezoelectric coefficient is greater than D31. However, D31 is more natural way of excitation for civil structure. Use of embedded sensors. These are concrete vibro sensors specially designed for RC structures. This is a patent product of our lab by my professor. This is developed for RC structures and they provide protection against environment. This is the brief outline of the video. These are the subparts of the video. It will contain a complete setup, damage description, then loading description, and giving a sine wave to the shaker, beam under vibration, voltage across the sensors, power measurement, energy harvesting, and SHM using 85933 and future work. One-third length of the beam. This is to create a damage condition. This is an inertial type shaker developed in our lab. It has been transformed from a contact type shaker. The benefit of this inertial type shaker is that we can enhance the force transmitted to the beam, which was earlier 98 newtons in case of contact type shaker and 108 newtons in the inertial type shaker. Now, the principle of which this shaker is working is that the vibration of this inertial mass, which is the plate in this case, is transferred to the beam via these four springs. The additional mass can be increased or decreased by adding or removing these extra plates developed for additional masses. These are the different type of electrical signals which can be given using this function generator. We will give a sine wave. So, we will give a 10 volts peak to peak voltage and a frequency of 16 Hz. Switch on this output and slowly increase the gain. If you connect any of the sensor with the oscilloscope, we can see a sine wave signal when I switch on the output, which dies down as soon as I switch off the output. Next step is to measure the energy or power generated by the sensor. For this, we have fabricated a circuit in our lab. Since the current is very small across the sensor, so it's very difficult to measure the current. So we have fabricated this circuit using which we will be measuring the voltage across the resistor R1 and then calculating the current. Here PZT patch is attached and here output across resistor R1 is measured. As soon as I switch on the output, this is the voltage signal which is seen across is to store that energy. For that, we have fabricated a full wave bridge rectifier circuit. We have connected the PZT patch here, and we are measuring the voltage across this capacitor. Here, yellow line represents the input voltage across the PZT patch, and blue line represents the capacitor voltage. Now, when I switch on the output, we can see the increase in the input voltage across the PZT patch, and we can also observe the charging of the capacitor. When I switch off the output, the capacitor gets discharged and the input signal dies down. An 85933 circuit, which is an alternative circuit for LCR meter. For starting this circuit, it has to be first calibrated with a 200 kilo ohm resistor. So we'll connect this resistor with the circuit and we'll give a start frequency of 50 kilohertz and a delta frequency of 200 hertz. Number of increments are okay, and we'll give internal oscillator, then start the program device registers, okay, calculate gain factor, okay, then measure the temperature, enable the theoretical calibration profile, and start sweep. Now this blue line is the calibration curve and black is the actual reading, so they should be very close to each other. Calibration part is done, so we will remove this resistor and will attach the PZT patch. Measure the temperature of the PZT patch, start the sweep, and now we can download the data in the Excel file. We are planning